Alright, in this example we're going to take a look at conceptually solving the problems and trying to understand it without doing any numbers if we can possibly get away with it. Now, there are a couple of things we can kind of figure out actually pretty quickly. Note, for instance, this is a pretty symmetric truss. If we were to sum forces in the x direction globally, we'd find out, of course, that Bx was 0. And then you look at By and JY, and note the 12 kilonewton load is right on the line of symmetry, so half of its load is going to go to either side. There would be a 6 and a 6, and then this other 12 kilonewtons is at the 1/4 3/4 point, and so 3/4 of its load, or 9, is going to go over to one side, and 1/4 will go to the far side. That's the way that would really work out. Of course, we could sum moments about point B to verify that. That's really what I was doing, was figuring that out really quickly, right? And so note again that middle 12 kilonewton load, its moment arm is half of what this big long one is. That's why it gets split evenly between these two supports, and then this other one has a moment arm that is 3/4 of what this other one is. So that would mean that it splits between 1/4 3/4 of the load, 3/4 going to the nearest support. Sort of an intuitive feel and sense of that. Right, so now let's actually address the real question of, well, let's find the free body diagram that will help us to figure out the force in member CD and the force in member DF and the appropriate equations that we would need with that. And as soon as I see something like this, because I'm always thinking, what's one single cut that I could make that would give me a free body diagram that will only expose those, and bam, look at this right off the bat. If I cut diagonally, I don't have to cut vertically, I just have to cut all the way through the structure, then note what we're going to get as our free body diagram. We'll have the AD portion here. Let's get our scale better. That's a little better. Alright, now we've got, there's AC, the top chord, there's the vertical CD, and there's the chord force DF. Right, and we know we've got this reaction. I know I said I wasn't going to do numbers, but it was so easy I just did it. And then we've got that top chord, which is probably in compression. That's FAC. We got the bottom chord, that's probably in tension. That's FDF. And then we have the vertical. Well, gee, is that going to be compression or is it going to be tension? Well, take a look. Simple summation of forces in the Y tells us that, hey, that's got to be going down. And so, wow, we just answered a whole bunch of things all at once. Sum of forces in the Y is the appropriate equation that we need. We can take upwards positive. That would be 9 minus FCD would be equal to 0. And bam, you'd have FCD value, right? So we've got one of them, and then let's see here. Select the appropriate equation you need to solve for FDF. Well, looky here. If we sum moments about point C, and let's say counterclockwise positive, then we're going to have AC and CD go away. Note the moment arm, or the point that we're taking the moment about, does not have to be on the free body diagram. It can be anywhere we want, and we're clever. We select ACCD to be that place, and then you'd have here minus 9 times, let's see, the panel is at 2.4. We're only one panel over, so that's 2.4, and then plus, the height of this is 1.8, so 1.8 times FDF, set it equal to 0, and that would be a one equation, one unknown in each instance. Simple, easy to solve for. So, hey, I like that. Pretty good.